Welcome back. We are talking about wastewater treatment, under which we are discussing about the secondary treatment operations. In this video, we'll be talking about the activated sludge process design parameters. So, this is the activated sludge process. This was discussed in one of the previous videos, where some portion of the sludge from the secondary sedimentation tank is recycled back into the treatment system, and thereby the solids are maintained at the concentration of mixed liquor suspended solids, and this will improve the efficiency of the treatment process. So based on this information, we are going to talk about some specific design parameters. The major design parameters include how much should be the detention time in the aeration tank, how much should be the sludge discharged or going outside, how much should be recycled, how much concentration of solids should be maintained, what should be the active life of the biological solids. These are the major parameters we should talk about. So now let us look at some of the conversion factors. Here are the operating parameters, design parameters. Here, if you look at the BOD load entering into the aeration tank, the first thing what we should know is BOD load entering into the tank. This is calculated as a flow rate multiplied by BOD concentration. So Q is the volume flow rate, and Y naught is the concentration of BOD. So here Q is also equal to this is also equal to Q into S naught, where S naught is the soluble BOD and Y naught is the 5-day BOD. We'll discuss about soluble BOD at later stage, but initially the soluble BOD S naught can be considered equivalent approximately to that of Y naught. And the only thing is, the units of conversion should be taken care of. Normally, we express discharge in terms of meter cube per day and BOD concentration in milligram per liter. So volume units are different here, meter cube and liter. That conversion factor should be used here, and milligrams also should be converted into kilograms. So here you are going to make use of these conversions. 1 meter cube is equal to 1000 liters. 1 kilogram is equal to 10 to the power of 6 milligrams. And day to hours conversion also sometimes we may have to do. Then MLSS concentration, we normally write this as X milligram per liter. Solids loading in aeration tank is nothing but how much is the volume of the tank multiplied by the aeration tank MLSS. So meter cube into milligram per liter. So influent solids loading is equal to Q into X naught. So how much Q is the solids volume discharge, and solids loading is QX naught. Effluent solids leaving, how much solids are leaving here? Q minus Q naught, Q minus QW is the effluent discharge going out, and Xe is the concentration of the solids. You multiply both, you are going to get effluent solids leaving. Solids wasted from the system, from the bottom, QW into XR. QW is the discharge and XR is the concentration of this sludge solids. So QW XR. Then hydraulic retention time. How much time we are retaining the water in the aeration tank? So this is nothing but volume of the tank divided by discharge. Q is the discharge entering and V is the volume of the tank. So V by Q. So again here time conversions. Q is given in meter cube per day, and volume in meter cube by meter cube per day will give you in terms of days. HRT normally is expressed in terms of hours. So hours to days conversion we have to make care of. And mass of solids in the system, how much of the concentration of solids are there in this tank? Volume of the tank is V, and solids concentration is X, MLS's concentration is X. So it is called Vx. Solid is wasted from the system. There are two ways you can see from the boundary. So now one is going through effluent and another going through the sludge cycle. And here what we are seeing is Q minus QWXE is the solids going out from the effluent system, and QWXR is going out from the sludge cycle. Solids retention time, SRT, this is the most important. So HRT is nothing but only volumetric flow. How much hydraulic retention time, how much water is retained, only one flow through cycle. But here the active life of the biological solids is more than what we normally have in the retention time for aeration tank and clarifier. So that's why this is solid retention time is more important. It's called as active life of the solids in the system divided by solids wasted from the system. That is nothing but how much is solids present here, Vx, divided by what is leaving, Q minus QWXE plus QWXR. So here, XE and XR, the concentration of XE will be very, very small. XE will be very, very small compared to that of XR. For example, the normal values, if you consider, the XE value will be around 20 to 30 milligrams per liter. 20 to 30 milligrams per liter. Whereas the XR concentration will be in the range of 10 to 12,000 milligrams per liter. So that's why we can ignore the value of XE for practical calculation point of view. So once we neglect that, so this term will get cancels. This term will get cancels out, and leaving SRT is equal to Vx by QWXR. This is approximation. And recycle ratio, that is more important here. How much is recycled back? Actual flow is Q and recycled discharge is QR. How much is recycled is nothing but QR divided by Q, which is called as recycle ratio. And another thing is F by M ratio. What is the meaning of F by M ratio? Food to mass ratio. How much is the food available? Food availability is based on the organic matter present in the wastewater. Organic matter present in the wastewater means that is nothing but the BOD. How much BOD is coming into the system and how much of microorganisms are there in the reactor? That is nothing but aeration tank. The biological solids or microorganisms present is nothing but MLSs. MLSs is there in the tank. So F by M ratio is nothing but how much BOD is coming, how much of MLS is there in the aeration tank. So that is nothing but Q into L naught divided by V into X. Divided by V into X. Simple calculation. The other words important is how much of oxygen you have to supply. There are two mechanisms we are using. One is a complete mix process where entire things are under complete mixing through a central aerator. Another one is we are sending air from the bottom through a diffuser. The two systems are there. So now oxygen requirement in the tank, we can calculate as the amount of ultimate BOD removed in the tank minus mass of the solids wasted. Okay, the oxygen is required only for the conversion, the removal of BOD. But at the same time, some portion of solids, they are wasted from the system. So we have to account for that. So 1.47 Q into L naught minus LE, this 1.47 is nothing but conversion from 5-day BOD to ultimate BOD. And 1.42 into Vx by SRT, in this 1.42 is nothing but the fraction of the waste converted into the wastage of solids. So for complete mixed reactor, the oxygen transfer efficiency, how much oxygen is required, okay. how much amount of aerators we have to convert, we have to keep in the tank. This is based on oxygen transfer efficiency of the aerators. So usually in operating conditions, 1.2 to 2.4 kilograms of oxygen per kilowatt hour is the oxygen transfer efficiency. But still we have a standard formula to calculate the oxygen transfer capacity under field conditions. So N is equal to Ns into Cs minus Cl by 9.17, 1.024 to whole to the power of T minus 20 into alpha, where N is the field transfer capacity of oxygen. Ns is OTE under, OTE is nothing but oxygen transfer efficiency. OTE under standard conditions in terms of kilograms of oxygen per hour, and Cs is the saturation DO value, in the aeration tank at operating temperatures, and then Cl is nothing but operating DO level in the aeration tank, and 9.17 is the saturation DO value in the water at 20 centigrade, and T is the temperature of sewage, where alpha is a correction factor for oxygen transfer efficiency, and is 0.8 to 0.85. The oxygen transfer efficiencies usually they are given by the supplier. If the data is known, we can make use of this equation. If the data is not known, we can straight away use these empirical values between 1.2 to 2.4, and usually we adopt around 2 kgs of oxygen per kilowatt hour. Using this, we'll calculate the power requirement, and in terms of HP also we can convert that value. Mixing requirements. To make all the things under suspension, it requires around 15 to 26 watt per meter cube of tank volume. The other option we have is the diffused aerators or plug flow system. There are two types of diffusers normally used: porous tube diffusers and coarse bubble diffusers. So now you can see here there are plate diffusers, and plate diffusers are there, the plates are there, they're having a size. And usually plate diffusers 0.3 meters by 0.3 meters into 25 mm size thickness, having a pores of 0.3 mm, and they release 1.22 to 1.2 meter cube per minute of air per meter square of a plate area. And spacing of the diffusers usually we keep at 0.6 to 1 meter. And porous diffusers and coarse bubble diffusers 6% and 8%. Now coarse diffusers, you can see this is a mushroom type of device, and where the number of holes are there here, and at the bottom the air will come through the bottom here, and they'll release it from the top like this, and then you can see that the tubes are there. The tubes, the end is open here, and from which the air is also coming out into the aeration tank. So tube diffusers are usually 0.6 meters long, internal diameter 50 mm to 75 mm, and usually the air supply must be at least 0.25 meter cube per minute per meter length of the channel, and they will be installed at 0.3 to 0.6 meters above the floor of the aeration tank, so that cleaning point of view, it will not create any disturbance. The most important observation is porous diffusers, they're having very small pores. Though they are efficient, but they are liable for more clogging. Now we'll have the overall BOD removal efficiency. That is one parameter. We can see that what is the initial value of the BOD entering into aeration tank, and what is the BOD value leaving, L0 and LE, and the difference with respect to initial value of BOD entering into aeration tank L0. We take that percentage, that is the overall BOD removal percentage. And these are the design parameters of the activated sludge process, water we discussed. And there are, you can see complete mix process. This is a complete mix process, plug flow process, and extended aeration. So this is extended aeration, another process that is also based on the complete mix process. So here the MLSS concentration will be around 3,000 to 6,000 milligrams per liter. HRT 3 to 5 hours, and SRT, you remember here, this is what I was mentioning about. This is the active life of the biological solids or microorganisms to be kept in the activated process, sludge process system. This is in terms of 5 to 15 days, whereas this is only 3 to 5 hours. That's important here. F by M ratio 0.6 to 0.2, and then recycle ratio around 0.25 to 1. This 25 to 100%. And volumetric loading, and the BOD should not be loaded too much per unit volume of the tank. So it is around 0.8 to 2. BOD removal percentage, that is nothing but overall BOD removal percentage in terms of 5-day BOD, 85 to 95%. Oxygen required, these are all checkpoints. Oxygen required kilograms per kilogram of BOD5, and the air requirement meter cube per kilogram of BOD. So while doing all the design calculations, so we need to have a glance at these values, and accordingly we have to assume the range of these values. Then we do the calculations and perform the necessary checks. These tables are more important in the design of the activated sludge process.